derivatives of the, I forgot my little clicker dongle today, so I got to do this and this, all right? Learn about the exponential functions. We talked about those before, but now we're going to learn how to find the derivatives of those functions. And then we're going to look at the logarithmic functions. Those are the inverses of the exponential functions. And we'll learn a fun new technique called logarithmic differentiation to find derivatives of these functions. Okay. So let's remind ourselves what we did all of 12 days ago when we were last here together. We did sections 3.1 and 3.2 about exponential functions. So an exponential function is something that depends on a positive base. We call that base A. And the conventions that we have in place are that if you have a positive number exponent, a positive whole number exponent such as 3 or 4 or 127, then a to the n means write down a at n times and multiply them all together. Of course, we don't have an idea for what that would mean if you had a power of -3 or of 4/5. You can't write down 4/5 of an a and multiply it together. So the other exponents have different interpretations. A to the 0 will always take that to mean 1. Or if n, the power is a negative number, we'll think about that as a reciprocal of the corresponding positive power. So a to the -4 means write down 4 a's, multiply them together, and then take the reciprocal. And then anytime you have a root, you can express that as a fractional exponent. So a to the 1/4 means 4th root of a, and a to the 3/4 means 4th root of a quantity cubed, or the 4th root of the quantity a cubed. And if you think about those power functions, that allows you to determine a to the r when r is any rational power. And there's only one continuous function which interpolates all those values, and we call it the exponential function with the base a. So these properties of exponentials are things that we sort of noticed to be true when the exponents were positive whole numbers, and then we wanted them to stay true when we extended our definitions to negative numbers or fractional numbers. So it's still true that a to the x plus y is a to the x times a to the y. And this is really the characteristic property of exponential functions. They convert addition into multiplication. They convert subtraction into division. Repeated exponentiation transfers as multiplying the powers together, and you can distribute a power across the base. Okay? So we did all of those 2 Wednesdays ago. And here's a graph of lots of different exponential functions. 2 to the x is this one here. 1/2 to the x is this one here. It's the mirror image of 2 to the x in the y-axis. And that's because 2 inverse, or 2 to the -1, is 1/2. Okay, here's 3 to the x, 10 to the x. And in between 2 to the x and 3 to the x, you see e to the x. What's e to the x? E is this magical number we define to be the limit as n goes to infinity, 1 plus 1 over n to the nth power. Why is it so magic? Well, as n goes to infinity, the base here goes to 1, and you know that 1 to any power is going to return 1. So it looks like this limit would be 1. On the other hand, we're taking it to a larger and larger power, and if you take a number that's bigger than 1, even if it's 1.1 or 1.01, and raise it to ever higher powers, you'll get something that goes to infinity. So the base is going to 1, which would make us think the limit would be 1. The power is going to infinity, which would make us think that the limit is going to be infinity. But it turns out that there's a finite non-1 limit here. Another way to express this limit, as we saw earlier, is the limit as h goes to 0 of 1 plus h to the 1 over h. Okay? 2 forms of the same limit. Now, we can plug it into some computer algebra system or Wolfram alpha and come up with values of 1 plus 1 over n to the n when n is large. And you see that it doesn't go to 1, and it doesn't go to infinity either. It converges to something like 2.718281828, 459.045, et cetera, et cetera. It turns out that e is not a rational number. It's not a fraction of 2 integers, nor is it an algebraic number like the root of a polynomial or anything. It's what we call a transcendental number, and as important among the numbers as pi is. The logarithms, anytime you have a power function, you can consider its inverse function, and the inverse function to the a to the x function is the logarithm base a of x. So to say that y is equal to log base a of x is precisely the same thing as saying x equals a to the y. Okay, anytime you have an equation that looks like this, you could rewrite it like this immediately. And in particular, for our favorite base, the number e, we have a special name for the inverse function that's called the natural logarithm. Log to the base e is known as the natural logarithm, and it was given that name by Euler, and he wrote it in French, logarithm naturel. Okay. And we learned lots of different properties of those logarithmic functions. Basically, any property of exponential functions, if you reverse it, you get a property of logarithmic functions. So we learned that a to the x plus y is equal to a to the x times a to the y. That is, exponentiation converts sums into products. Logarithmification turns products back into sums. So the log of a product is the sum of the logs of the factors. The log of a quotient is the difference of the logs. And the log of a power is that power times the log of the base. That exponent times the log of the base. Okay, and these are graphs of the logarithmic functions. I've drawn them in blue here. They are inverses of these green functions. So this is 2 to the x. Its inverse is log base 2 of x. Here's 3 to the x. Its inverse is log base 3 of x. E is in between 2 and 3. So e to the x is in between 2 to the x and 3 to the x. And the same is true for the log base e of x. It's in between log base 2 and log base 3. Okay? But all these logarithms do basically the same thing. They go up like this, and then as you go further and further out, the tangent lines become less and less steep, and so they're pretty much all the same. They all go through the point 1, 0 as well. And the reason that they all look very similar is because of the change of base formula. If you have logarithms to one base b, and you would like to compute them to another base a, you can do that by taking the log base b and dividing it by the log base b of that other base a. So if I have a button on my calculator that does log base 2, and I want to compute log base 10, I can do that by simply dividing by the log base 2 of 10. So all of these logarithmic functions are really just multiples of each other. So you only need to know one of them, and which one you pick is a matter of convention. Engineers like to do the log base 10. They call it the common logarithm, and they write it log. You might have an log button on a calculator that's computing log base 10. Computer scientists, because they measure algorithms which do a lot of division in 2, and because they do all their binary arithmetic, they like the binary logarithm, which is the log base 2, and they will sometimes write it as lg. We mathematicians have our own special reasons for preferring the base e, and as we said, Euler and us will call the log base e the natural logarithm, and I'll write it as ln. Okay, so that was our crash review of the previous 2 sections 12 days ago. Questions? All right. Remember all that? That was awesome. Okay. Well, then let's talk about calculus. We didn't talk at all about calculus on Wednesday. We're really only defining these functions and looking at their properties. So what about derivatives of these functions? For instance, the derivative of an exponential function. Well, let's remember how we can find the derivative of a function. Write down the definition of the derivative. It involves a limit, and then see what you can find out from the limit. Okay, here's the rabbit pulled out of the hat. The derivative of an exponential function a to the x is the derivative at 0 times a to the x. And why is that true? Starting from the definition of the derivative, f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. This limit is an important symbol. It tells me that I'm not just considering a function, but the limit of this function as h goes to 0. Plugging in what our function actually does, f of x plus h is a to the x plus h, f of x is a to the x, and then we divide that by h. Okay. Can we let h go to 0 and just plug it in? No, because then the denominator will have a 0 in it. We also can't do that in the numerator because we have a 0 in the numerator, and 0 over 0 doesn't have any meaning. But that's actually a good sign. It means that we might get an actual limit here. Using the property of the exponential function, I mean, pretty much the sine qua non of exponentiation is that it converts addition into multiplication. So a to the x plus h is a to the x times a to the h. And we subtract from that a to the h, divide by subtract from that a to the x, divide by h, and hopefully this is going to have a limit. Well, if you stare at this a little bit, you see, okay, I've got a to the x in this piece of the numerator, and a to the x in this piece of the numerator, so I can factor out a to the x. And the limit is not a limit of x. X isn't moving. It's a limit of h. So as far as h is concerned, x is constant, and anything involving x is also constant. I can factor that out of the limit. And what I'm left with is the limit as h goes to 0 of a to the h minus 1 over h. Okay, now what is that limit? Well, a to the h sounds like f of h for some number h. And what's 1 f of? Well, 1 is f of 0. So this looks like f of 0 plus h minus f of 0 divided by h. So this limit here is a derivative of the function f at one point, that is the point 0. Okay, so what have we done here? We've evaluated the derivative of the exponential function with base a. So far, all we've said, though, is that it's a to the x times some other unknown number. But this is actually kind of significant, because the function that we are finding the derivative of is a multiple of itself. Think about the other functions that we've found derivatives of in the past. The derivative of a polynomial function, such as x cubed, is that a multiple of x cubed if you take the derivative? Not a constant multiple of x cubed, right? The derivative of x cubed is a multiple of x squared. The derivative of x to the 12th is a multiple of x to the 11th. So the derivative of the sine function is not the sine function, it's a cosine function. The derivative of, what else do we know derivatives of? Derivative of x to the 1/2 is x to the minus 1/2. This is the only function that we can think of whose derivative is a multiple of itself. I mean, there are others, but essentially it's the exponential function and nothing else. So that's significant about exponentials. Their derivatives are multiples of themselves. Now, what about that limit? We said that the derivative of a to the x is a to the x times some constant. That constant is a limit. As h goes to 0, a to the h minus 1 over h. When a is e, we've already computed this limit. Remember what we did? We did this 12 days ago. Anyone remember what the limit as h goes to 0 of this is? It might even be in your notes. The limit is not e. It's a good guess. It's not 0. It's not infinity. It's 1. That's right. The limit is 1. And the reason is basically from the definition of e. If we write it instead of this way as this way, the limit as h goes to 0, 1 plus h to the 1 over h, then for some small number h, we can approximate e by 1 plus h to the 1 over h. And then if I take that 1 plus h to the 1 over h to the h minus 1 divided by h, then it basically unravels everything we did to 1 to start with. Take it to the h, that cancels the 1 over h exponent. Subtract the h, and it leaves an h in the numerator. Divide by h, and we have a 1 as a quotient. And so the limit is going to be approximately 1, and in the limit it's exactly 1. So the funny limit, e to the h minus 1 over h, turns out to be exactly 1. And that tells us that the derivative of the exponential function when the base is e is 1 times e to the x. In other words, the derivative of e to the x is 1 times e to the x. And this is one reason we love the base e so much. The derivative of the exponential function with base e is that same function. Okay? No constant floating around. The constant is 1. We don't even have to write it. Okay, so this is why the exponential function is so cool. This is why the exponential function is so useful, because all around us there are things which grow in proportion to their current quantities. For instance, if you think about bacteria in a petri dish, small bacteria, large-ish petri dish, then bacteria are reproducing asexually, so at any given time, any one of these bacteria could be reproducing and popping off little baby bacteria. So the amount of new bacteria you have in a culture of bacteria is proportional to the amount that you have already. Lots of bacteria, lots of baby bacteria. Less bacteria, less baby bacteria. No bacteria, obviously no baby bacteria. So the more you have, the more you will increase. And what that's saying is that the bacteria satisfy a differential equation very much like the exponential function. Its derivative is a multiple of itself. Okay. Other things which increase exponentially is money. We did that extended example with money in your bank account. Right? The amount of interest you get is proportional to the amount of money you have in the account in the first place. And so the amount of money you will get grows exponentially. Your social networks can also grow exponentially because the more friends you have, the more connections you make, the more new connections you are exposed to. And so you add on friends who are friends of your friends, and so on. I think also language usage grows exponentially, at least at the beginning. We've seen a misuse of exponential growth a lot in colloquial speech. Someone will say it grows exponentially to mean it grows a whole lot. Maybe not according to a law like this, but they will say exponential. Okay, so that's why we care so much about exponential functions, that they describe a lot of the world around us. Now, let's think in practical terms of differentiating a function with an exponential. The derivative of the function e to the 3x. How many are still on spring break, by the way? Okay, I can tell. What rules do we need here when we're differentiating e to the 3x? Yeah? The chain rule, right? Not just the derivative of an exponential, but we're combining that now with the derivative of 3x. So the derivative here is going to be e to the 3x times the derivative of 3x, and that derivative is just 3. So the answer we get is 3 e to the 3x. Make sense? Okay. Well, how about this one then? The derivative of, are you guys still writing that one? Derivative of e to the 3x is 3e to the 3x. The derivative of e to the x squared, kick it up a tiny notch. Sorry. Sweep out the cobwebs from the corners of your differentiating brains. So, anyone got an answer here? 2x times e to the x squared. So the derivative of any exponential function is itself, but because that exponent is a function, we need to use the chain rule and multiply by the derivative of that function. So we get e to the x squared times the derivative of x squared, and the derivative of x squared is 2x. And it just seems prettier to write the 2x in front of the e to the x squared rather than this in back. So I did it that way. Okay, here's another one, the derivative of x squared e to the 2x. I know spring break was enjoyable for me too. I got to sleep in till 6 a.m. every day. Did you get it, Marco? Okay, so he's got e to the x times 2x plus x squared. Anyone get anything different? X squared e to the x plus 2x e to the x. Those are the same. He's factored and you've multiplied out. So yeah, there you go. What rule are we using here? We're not using the chain rule, we're using the product rule because we're multiplying x squared and e to the x. I guess the only thing that's kind of confusing about this problem is that it looks like we left x squared alone, and then we differentiated x squared, but it looks almost as if we forgot to take the derivative of e to the x. But we did. We took the derivative of e to the x right here. The tricky thing is that the derivative of e to the x is e to the x. And so, it doesn't look like we did anything, but we did. So yes, you can factor. There's no accounting for taste, right? Either way, if you want to factor, you certainly may. Okay, So any other questions about derivatives of exponential of the v function e to the x? Okay. If you are trying to memorize derivatives, that's the easy one to memorize because its derivative is itself, and that's what makes it so special. Let's look then at the derivative of the natural log function. That's the inverse of e to the x. Now, we've used the technique of implicit differentiation sometimes to find derivatives of inverse functions, and we'll do that here. If we want to find the derivative of the natural log of x, let's first rewrite it as x equals e to the y. Why? Because we can. Also, because I know how to find the derivative of the exponential function e to the y, I don't yet know how to find the derivative of ln x. But I can take this equation and find the derivative, remembering that y is a function of x. So I'll use implicit differentiation. Implicit differentiation says take the derivative of e to the y, which is e to the y, then the derivative of y, dy dx. Okay, chain rule coming into play there. On the other side, I need the derivative of x, which is just 1. So the equation becomes e to the y, dy dx equals 1. What was it I wanted to find in the first place? I want to find dy dx. So let me solve this equation for dy dx. And the answer I get is 1 over e to the y. And e to the y is x. So it's 1 over x. Are we done? Yes, we are done. We found the derivative of the exponent of the natural log function. The derivative of natural log of x is 1 over x. Isn't that cool? Well, let's see. Is it really cool? Here's the natural log function. Okay, and a couple of things you can see about the natural log function are that one thing is always increasing, right? Always increasing. The amount it's increasing is very large here, and the amount it's increasing is very small here. The further out I go, the less it's going to increase. Let's look then at the graph of 1 over x, and it has those properties that we would expect from the derivative of this blue function. First of all, blue function's always positive. I'm sorry, always increasing. So the red function, its derivative, is always positive. That's what we expect. Increasing function, positive derivative. It's increasing a lot here, and the derivative is very positive here. It's increasing not so much over here, and the derivative is not so positive over there. Okay, so it's behaving exactly like we would expect the derivative of the natural log function to behave, and it also fits in very nicely with what we were calling the tower of powers. Remember, of course you remember, the derivative of x cubed is x squared. Okay, not exactly, but it's a constant multiple of x squared. The derivative of x squared is x to the 1, okay, times a constant. The derivative of x to the minus 2 is a constant times x to the minus 3, and all of those power functions had power functions as derivatives. But there was one power function which did not have a power function as its derivative, and there was one power function which was not the derivative of another power function, and that was x to the minus 1, 1 over x. Okay? If you tried to find a power function whose derivative is x to the minus 1, what you end up with is dividing by 0, and we know that's bad. Okay? Natural log of x fills in that gap very nicely. It's sort of the missing power function. All of these power functions decay because they're reciprocals of power functions up here. These all go to infinity. These all go to 0. Natural log fits right there in the middle of those. Okay, so that's why we care about the natural log function. It's the inverse of the exponential function, and it's the missing piece in the tower of power puzzle. Its derivative is 1 over x. All right, now that we know that, we can find derivatives of these functions. I'll give you 3. Natural log of 3x, x times natural log of x, and the natural log of the square root of x. Do the first one first. first one first. Let's find the derivative of natural log of 3x. Anyone want to shout out an answer? Yeah?
3 over x.
3 over x. Do we get any other answers? 1 over x. Any other answers? 1 over 3x. All right, we ran the gamut. How about 3 over 3x? I don't know. Okay, let's figure out what the answer actually is. The derivative of the natural log of 3x. What rule comes into play here? Well, you could use the chain rule, right? Because you're taking the natural log of a function of x. Natural log of 3x. All right, let's try that. Okay, so with the chain rule, you want 1 over 3x, and then you multiply by the derivative of 3. Well, the derivative of 3x, which is 3. Okay, 1 over 3x times 3 is 1 over x. So if you got 1 over 3x, then you probably forgot this part here from the chain rule. And if you got 3 over x, then you probably forgot this part down here with the denominator, right? The derivative of the natural log of any function would be 1 over that function times the derivative of that function. So we got 1 over x. Now, Marco, you wanted to double check with me. This was the answer you got, but you were a little bit worried that it was not right? Okay, so what's kind of surprising about this?
Well, it's the same as the natural log of x.
That's right. It's the same derivative as if we didn't have the 3 at all, right? The derivative of the natural log of 3x is the same as the derivative of the natural log of x. Let's take the derivative another way and see if that makes more sense. Okay, we know that the logarithms convert products to sums. So the natural log of 3x is the natural log of 3 plus the natural log of x. Now, what's the derivative of the natural log of 3? It's not 1 over 3, because 3 is not a variable, 3 is a constant. The derivative of a constant is 0. So the derivative of the natural log of 3, funny-looking constant though it is still going to be 0. Okay, so the derivative of log 3 is 0. The derivative of log x, we know, is 1 over x. And so we do get the 1 over x. So the reason that we still get 1 over x is that the natural log of 3x is the natural log of x plus a constant. Even though we haven't written it in that form, because the way logarithms work, that's how it works out. Okay, so that was a surprising answer, but if you think about it in a different perspective from identities of logarithmic functions, it's not so unexpected after all. Okay. How about this one? The derivative of x times natural log x. 1 plus ln x. Okay. Let's see if that does work out. We're using the product rule now. So the derivative of the product of two functions is the derivative of one of the function times the other. Then times the opposite process, leave the first function alone, take the derivative of the second. The derivative of x is 1. Leave the ln x alone. Leave the x alone, and then take the derivative of ln x, which is 1 over x. 1 times ln x is ln x. X times 1 over x is 1. And there you go. You got 1 plus natural log of x. Okay, which is kind of interesting, because you can use this fact to construct a function whose derivative is natural log of x. That's kind of cool. Okay. Tricky thing might be that the 1 over x and the x cancel each other out, leaving this 1 that sort of stays put. And it doesn't go away because we're not taking the derivative of 1. It just sort of shows up when we multiply x times 1 over x. Okay, questions about that one? Okay, let's try this one. Natural log of the square root of x. 1 over 2x. Any other answers? Okay, how did you get 1 over 2x so fast?
First, 1 over square root of x, like the natural log, and I multiplied it by the derivative parameter of x, which is 1 over 2 times x, and I multiplied and that cancels out.
So this is what you got? Yeah. All right. So the derivative of the natural log of any function is 1 over that function times the derivative of that function. Okay, so he wrote down 1 over the square root of x, then said, okay, now we have to take the derivative of the square root of x. And that's a power function. Its derivative is another power function. So it's 1 over 2 times the square root of x. If you like powers, then it's the derivative of x to the 1/2, which is 1/2 x to the minus 1/2, which as a radical would be 1 over 2 square root of x. And now the square root of x and the square root of x combine to give an x, and the 2 stays put, and you get 1 over 2x. Mm-hmm.
Can we also put the one, make it just ln x to 1 half and bring the 1 half down and then power rule?
Make it what?
And then make it a 1 half ln times x and then power rule.
Okay, we can make it a 1/2 times ln x. That's right. Yeah, the other way to do it would be to use the property of logarithm. This is x to the 1/2. So the natural log of x to the 1/2 is 1/2 times the natural log of x. Okay, and then we use the derivative of natural log, which is 1 over x. That was what you were saying, right? Okay, so the thing that was confusing me was that I wouldn't call this the power rule, but you're saying take the derivative of the natural log, and you do get x to the power minus 1. Oh, okay, yes, it's basically the constant multiple rule. Right. So again, if you do it the chain rule way, you'll get an answer which is kind of surprising, because this looks like a complicated function, this looks like a simple function. But if you use the property of logarithms way, then you get an answer which is not, well, you get the same answer, but it's not as surprising. Make sense? Other questions about these? Okay, it's this kind of thing where if you've done it before, it seems completely old hat, and it won't be too hard to remember again. If you're doing it for the first time, you think, oh, I'm never going to learn that, but you will. It just takes a little bit of practice. Luckily for us, there's a magical website which provides us oodles and oodles of practice. It's called Web Assignment. Okay, so let's then look, now that we've focused on the natural exponential function e to the x and the natural logarithm function log base e of x, or ln x, let's look at derivatives of exponentials and logarithms with different bases. So now the base is just going to be some number a. A could be 2 or 10 or something even stranger, but it's not going to be e necessarily. Okay, so how would we find the derivative of a to the x? One thing we could do is do a formal derivation like we did before, but now we actually know a little bit more than the last time we tried to find this derivative. We know the derivative of one exponential function. That function is e to the x. Jokes are up here, dude. I saw you laughing at your screen. I thought maybe you'd want to laugh at me instead. Okay. So let's find the derivative of a to the x. Solving that equation, y equals e to the x, well, taking the log of the equation, y equals a to the x, we get natural log of y is natural log of a to the x. Properties of logarithms tell us the natural log of a to the x is x times the natural log of a. Now, what kind of number is the natural log of a? I don't know, but I know that it's a constant. It's not a function because the variable is x. A is a constant. So I have the natural log of a. So this equation here is actually quite simple. The natural log of y is x times the natural log of a. That is x times a constant. And if I differentiate, the derivative of x times natural log of a is natural log of a. Okay? If that's confusing you, remember, this is a constant. So x times ln a is exactly the same kind of function as x times 4. So the derivative of x times 4 is just plain old 4. Now the derivative of the left-hand side, the natural log of y, is 1 over y, but because y is a function of x, I have to multiply by dy dx. And so what I get is 1 over y dy dx equals natural log of a. What did I want? I wanted dy dx, so let me solve this equation for dy dx. That is, bring the y over here. Natural log of a times y. This is a constant, remember. Natural log of a times a to the x. Okay, so almost magically, we've gotten the derivative of a to the x. The magic was that we applied the properties of logarithmic functions. Well, we took the log, applied properties of logs, then took the derivative, and out popped the derivative that we wanted. Okay. Now, we had said before that the derivative of a to the x was going to be a constant times a to the x, and we even determined that that constant was the derivative of the function at 0. So now I know that the derivative of the function a to the x at 0, that is the limit a to the h minus 1 over h as h goes to 0, is the number natural log of a. This gives me a nice experimental way to compute numerically natural logarithms. If I wanted to find the natural log of 2, I should take 2 to the h minus 1 over h for some small number 2, not a small number 2, a small number h, And in the limit, as h goes to 0, I get the exact natural log. So approximately 0.693 for the natural log of 2. Natural log of 3, take a small h, plug it in. You get something approximately 1.10. Okay. So if you wanted to find the natural log of 10, take a small number h, find the quotient 10 to the h minus 1 over h. Okay, so we learned the derivative of a to the x. Let's learn the derivative of log base a of x. Okay, how would we attack something like this? Well, we know the derivative of the natural log. We know the derivative of e to the x. We also now know the derivative of a to the x for any number a. So all of those we can use. Let's solve this equation in a form that we can find the derivative. So if y is log base a of x, let's write it instead as a to the y equals x. Why would I do that? Well, I know the derivative of a to the whatever. I just learned that. And I know the derivative of x too. So I can differentiate this equation implicitly. The derivative of a to the whatever is a to the whatever times the derivative of whatever. And then we also have this natural log of a constant floating in the front. The derivative of x is still 1. And if I solve that for dy dx, then I get 1 over a to the y times the natural log of x. 1 over a to the y times the natural log of a, constant, right? And then that a to the y I can sub in back for x. So from front to back, the derivative of the natural log function, the derivative of the log base a function is 1 over x with an additional constant of 1 over natural log of a. So if you look at these two that we derived before, and think about what happens when a is exactly e, we should get the rules that we had already. So when a is e, we would have natural log of e. And what's natural log of e? 1, almost by definition. And on the other end, we have 1 over x times natural log of a. If this were the log base e, I would have the natural log of e. The natural log of e is 1, so I would have 1 over x. Okay, so it does work out if in the other cases, which is good news. Okay. Another way to prove this derivative is to remember our change of base formula. The log base a of x can be written in terms of the log base e of x, and I already know the derivative of the log base e. Log base a of x is the natural log of x divided by the natural log of a. And that's constant. So the derivative of this function is 1 over the natural log of a times the derivative of natural log of x, which of course is 1 over x. So we didn't really have to do a whole implicit differentiation thing, just use the change of base formula. So any way you want to remember these things is fine. You can memorize them, or you can memorize the differentiation process. They're all very similar. Okay. How would we find the derivative now of the log base 2 of the function x squared plus 1? Why don't you try this one yourself? writing. I see that you've mostly stopped writing. Okay. You ready to go on? Okay. Many of you were staring at the screen hoping that the answer would magically appear. Okay, I can make that happen. Here it goes. There. Is this the answer you got? If it were the natural log of x squared plus 1, then you would take 1 over x squared plus 1. But because x squared plus 1 is still a function, you need to multiply by the derivative of x squared plus 1. That's 2x. Okay, so it would be 1 over x squared plus 1 times 2x. Now, it's not natural log of x squared plus 1. It's the log base 2 of x squared plus 1. And what difference does that make? Well, you have to divide by the natural log of that different base 2. So it's 1 over natural log of 2 times 1 over x squared plus 1 times 2x. And you, of course, can write that as a single fraction. Make sense? Okay, so it's not too complicated, except that we have all these things happening at once, right? Chain rule, natural log, not natural log, logarithmic function to a different case. Okay. So to recap, what we've done is the derivative of e to the x, the derivative of the natural log of x, and also derivatives of those same functions when a base is not e. Okay. So I want to look at a new technique of differentiation inspired by this nasty-looking derivative here. I'm not going to make you do this one on your own, but let's take a look at what we would have to do to find the derivative of this function. The function is x squared plus 1 times the square root of x plus 3 divided by x minus 1. Now, think ahead. What do we have to use in order to find this derivative? Well, it's a quotient, so we'll have to use the quotient rule. That will involve, in some way, the derivative of the numerator and the derivative of the denominator. The numerator is a product, so the derivative of the product is going to involve the product rule. And the derivative of the product will involve, not simultaneously, but the derivatives of each of the factors. So I'm going to have to take the derivative of this and the derivative of this. This is a power function with a power of 1/2, so that's going to need the chain rule. So we need quotient rule, product rule, and chain rule all at once to do this derivative, and this is what we get. Is that what you thought it was going to be? Well, this is the denominator times the derivative of the numerator, which involves the product rule, right? So this is 2x, the derivative of the first factor times the second, plus the first factor times the derivative of the second. And then we do the opposite differentiation, right? Here's the numerator times the derivative of the denominator divided by the denominator squared. And if you play around with this, multiply it out, and factor what you can, then you get something that looks like 2x times the square root of x plus 3 divided by x minus 1 plus x squared plus 1 divided by 2 times the square root of x plus 3 times x minus 1 minus x squared plus 1 times the square root of x plus 3 divided by x minus 1 squared. Okay. So if you're writing this down, don't worry, it will reappear on slides later on. So it's not going to disappear completely. What I want you to notice is that it took a lot of work. Right? We had to use quotient rule, product rule, and chain rule to get this all done. Now, here's another way that we can do the same derivative. We have this expression here, y is this product of x squared plus 1 and the square root of x plus 3 divided by x minus 1. If I were to take its natural logarithm, then I can use properties of natural logarithms to write this in a different way. The natural log of this numerator is the sum of the natural logs of each of its factors. Then I would subtract the natural log of the denominator. And that's because the log of a quotient is the difference of the logs of the numerator and the denominator. Okay, so the numerator is a product. Its log is the sum of the logs of the factors. And the log of x plus 3 square rooted is 1/2 times the log of x plus 3. So I've now taken the log of the whole thing and written it as a sum and difference of multiples of logs. If I were to do that, then I can take the derivative of each side here. The derivative of natural log of y is 1 over y. Because y is a function of x, I multiply by dy dx. And then the derivatives of each of these things, I can use the chain rule for it. The derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1. That's why we get this 2x. The derivative of 1/2 times the natural log of x plus 3 is 1/2 times 1 over x plus 3. The derivative of natural log of x minus 1 is 1 over x minus 1. That minus comes from the quotient, and it stays here in the derivative. Okay. Am I done? No, I want to dy dx, and instead I have 1 over y times dy dx. Let me just multiply by y. So dy dx is this whole stuff, sum of three fractions, times y, which another way to write that would be just to sub in what y is. And now I have an expression that just has x in it. Yeah? How does the derivative of ln x squared plus 1 equal 2x over x squared plus 1? Well, remember, we use the chain rule. So the derivative of natural log of x squared plus 1 is 1 over x squared plus 1. But then I have to multiply by the derivative of x squared plus 1, which is 2x. So I just wrote it as a single fraction rather than writing as 1 over something times something else. Okay. So I got this other expression for the derivative. It's a product of one thing, of y, with a bunch of fractions. Okay? Now, if you're copying this one, that's all right. It's going to appear at the bottom of this slide here. So this is our answer from the 2 slides ago. This is our answer from the last slide. And they're supposed to both be the derivative of the function y. Well, the function only has one derivative, so these should be the same thing. Are these actually the same thing? Well, if we were to multiply this out, would we get this one on top? Let's check. We've got a 2x here and a 2x here, so those check. We've got a square root of x plus 3 and a square root of x plus 3, so those check out. We have x minus 1, and there's an x minus 1 in the denominator that gets multiplied by this, so that works out. We have x squared plus 1 and x squared plus 1 in the numerator and denominator, and that's why we have no x squared plus 1 factor in this fraction here. So this fraction times this fraction does equal this fraction. Next one, x squared plus 1. Yep, there's an x squared plus 1 here. 2, oh yeah, there's a 2 there. Square root of x plus 3. Well, there's a square root of x plus 3 in the numerator and an x plus 3 in the denominator. So it's like x plus 3 to the 1/2 divided by x plus 3 to the 1. The result would be x plus 3 to the minus 1/2, and that's what that is. That's x plus 3 to the minus 1/2. So that's the same thing. Okay, what else? X minus 1 in the denominator, x minus 1 in the denominator. Last term here, x squared plus 1, x squared plus 1, x square root of x plus 3, square root of x plus 3, x minus 1 squared. Well, here's an x minus 1, and here's an x minus 1. So every term in the one expression matches with a term in the other expression. These are, in fact, the same thing, which is nice, right? You would expect to take the derivative 2 different ways. They should get the same thing. Now, which one do you like better? Do you like the old way, which involved the product rule and the chain rule and the quotient rule, or do you like this new way, which we call logarithmic differentiation? How many like the old way? Nobody? Okay, good. We got one person who was old school, right? How many like logarithmic differentiation? Okay, good. Logarithmic differentiation is pretty cool, right? Because we would much rather do the derivative of a sum than the derivative of a product, right? We'd rather use the sum rule, that's the easier one, than the product rule, that's the one that involves more terms, okay? And that's precisely what logarithms do. They convert products to sums, and they convert powers to constant multiples. We would much rather take the derivative of a constant multiple of a function than a power of a function. All right? So that's why logarithmic differentiation is so useful. What's it useful for? It's useful on functions which are built out of products of powers of functions. Right? So these algebraic kind of functions are good targets for logarithmic differentiation. Okay? Can't use logarithmic differentiation on any function. But if it's constructed out of products and powers and quotients, then it will be easier to use logarithmic differentiation because logarithms simplify powers and products and quotients. Okay, so that's good. These are the same, and this one is typically faster when applied in the right cases. Okay. Next question. Let's look at the function y equals x to the x. And we want to find the derivative of this function. Before we dive into the derivative, let's ask ourselves, what could it be? Well, one thing it could be is what you would get if you were to apply the power rule. X to the power x, let's use the power rule. That would say pull down the power and then subtract 1 from the power. X times x to the x minus 1. That simplifies back to x to the x. So one possible answer is that the derivative of x to the x is x to the x. Another answer that you might suspect is that this is a exponential function, right? There's a function in the exponent. So the derivative would be kind of like the derivative of a to the x. The derivative of a to the x is the natural log of a times a to the x. Maybe it's true that the derivative of x to the x is the natural log of x times x to the x. Okay? And if it's not one of those, I guess it's C, neither. Now, I've seen all of these on student papers, so I know that these could possibly be the answers in your head. How many think the answer is A? Okay. How many think the answer is B? Okay. The score is still 0-0. How many think the answer is C? Okay, we got 4. How many don't know? That should be everyone else, right? How many don't care? That should still be nobody. Okay, good. So a few people said it can't be these two. It has to be something else. And the rest of you don't quite know. Well, let's think about why answers A and B, though plausible, are not correct. Okay? Why is A not right? The answer is going to be C. So answer A was that y prime was x to the x. But x to the x is a positive function. And if you look at the graph here, you can see that it's not always increasing. Right? Function's decreasing here. So we know that its derivative is going to be negative, at least in this part. And that function, x to the x, is never negative. Okay, so x to the x cannot be the derivative of x to the x. Second guess, natural log of x, x to the x. Well, if you take this supposed derivative and plug in x equals 1, you'll get 1 to the 1, which is 1, times the natural log of 1, which is 0. And that would predict a horizontal tangent to the graph of the function at the point 1, 1. Well, here's the point 1, 1, and you can see that the tangent line is not horizontal at 1, 1. Its tangent line is horizontal maybe here, but that's not 1, 1, that's something else. Okay, so that's the reason that the derivative cannot be natural log of x, x to the x. All right, so neither of these is right. It's not x to the x, it's not natural log of x times x to the x. It's got to be something else. What is it? Well, we can find out what it is using our logarithmic differentiation technique. So if y is x to the x, then the natural log of y is x times the natural log of x. Right, the log of a power is the exponent times the log of the base. And in this case, the exponent and the base are the same thing. They're both x's. So natural logarithmic differentiation is when you take the natural log and then you take the derivative. So the derivative of natural log of y, this part doesn't change from problem to problem. It's always going to be 1 over y dy dx. 1 over y dy dx. The derivative of x times ln x, we've actually done that one already too. It's 1 plus natural log of x. Right? Product rule comes into play there. So the thing we want is 1 plus natural log of x times x to the x. And you can multiply that out as x to the x plus natural log of x, x to the x. Okay, never did my fingers leave my hands. Any questions about this one? Okay. And if it were more complicated function, you could still take its derivative using this process. Anytime you have a function which is a power function where the base and the exponent are both functions, then you can't treat it like it's a power function or like an exponential function. You have to do this logarithmic differentiation technique. Okay? And so something like that should work. Now, if we go back to the graph and see, does it have the properties that we would expect? Well, 1 plus ln x times x to the x is not always positive. It's possible for ln x to be negative, in fact, even less than 1, and that will make this factor negative. Multiply by a positive, we will get something negative. So it does work. When is this 0, by the way? When is 1 plus ln x equal to 0? 1 plus ln x equals 0, ln x equals negative 1, and what x has the property that its natural log is minus 1? Can you take negative e. No, you can't take negative e, but you can take e to the negative 1. Right? E to the negative 1 is the number whose natural log is negative 1. And e to the negative 1 is the same thing as 1 over e. That's a number in between 0 and 1. Okay? So what's kind of cool is that we get the x to the x term, which was the first wrong answer, and we get the natural log of x times x to the x, which is the second wrong answer. Both of those are the answer. Add those two together, and we get the correct answer. So two wrongs do make a right in this case. Both of our wrong answers sum up to the right answer. And this function is the one that behaves like we would expect. On the interval 0 to 1 over e, this term is negative, and so the derivative is negative. And we see that because the function is decreasing up to a point. And when x is exactly e to the minus 1, this term will be exactly 0. And so we'll see a horizontal tangent. And that function does have a horizontal tangent right around here. 1 over e is kind of close to 1/3, right? Because e is pretty close to 3. And that's kind of where we see our horizontal tangent. So that does jibe with the graph. And it's kind of cool that we added our two wrong answers to get the right answer. Okay? Other questions about that? Like I said, if you have a power function where base and exponents are both functions, you'll need to use logarithmic differentiation to find its derivative. Okay. We did all that. All right. So let's go back to the power rule, because you know how much I love the power rule. We have proven the power rule in many different ways. When we first did section, what was it, 2.2 or no, 2.3, we proved the power rule for positive whole number powers, 4, 6, 112, whatever. And we did that by using Pascal's triangle. Okay, and we just expanded it out, and we noticed that the first term was going to cancel, and the second term was going to be a multiple of the one lower power. And then we learned, we learned the product rule, and we learned the quotient rule. The quotient rule allowed us to take derivatives of power functions when the power was a negative whole number. And the constant rule allows us to take the derivative of x to the 0. And what else? The chain rule and or implicit differentiation allowed us to take derivatives of x to the r when r was a fraction. How will we take the derivative of x to the r when r is an irrational number like pi? Well, I have a technique of differentiation which does not depend on the power at all, and it's this logarithmic differentiation. If y is x to the r, then the natural log of y is r times the natural log of x. Okay, take the derivative of this equation. The derivative of the natural log of y is 1 over y. The derivative of y is dy dx. And the derivative of r times ln x is r times 1 over x. R is constant, right? So its derivative just multiplies the derivative of everything else. Solve this for dy dx, and you get r times y over x. Y is x to the r divided by x, and you get x to the r minus 1. And there you have it. The derivative of x to the r is r times x to the r minus 1. And we didn't make any assumptions about r other than this power function is defined. Okay? So there is the power rule in complete generality. Okay. So we did a lot, right? We did the derivative of e to the x and its inverse function. We did the derivative of a to the x and its inverse function. We learned this new technique of logarithmic differentiation, which allows us to take derivatives of functions which have lots of nasty powers and quotients and products in them. And we finally dispensed with the power rule. There are no more new ways to prove the power rule. We have done it now for all powers, positive, negative, rational, irrational, whatever. Okay? You want to go back to this one here? Okay. So I'm done. You have 6 minutes to frolic with your friends. And I'll see you on Wednesday.